Jnanam paramam dheyam. Knowledge is supreme.
Okay, so I am going to get on to the linear vector space today, and that is the main theme in quantum mechanics. We are going to mechanically follow a notation or a language, and you need to get used to this language. So I will go slowly on this language by showing analogy with your conventional 3 dimensions. Some problems were already given in conventional 3 dimension, right? Why is the 3 dimensional space called as a vector space? So you have vectors, linear combination of 2 vectors, which is going to give you another vector which is an element of the linear vector space. Let me call it as capital V. So set of vectors belong to a space which I will call it as the vector space V, and A plus B should be C. Some scalar multiplying A plus B will satisfy, is that right? What else? Can also have A plus B plus C satisfying associativity property, right? And vector addition, they are commutative in the sense the order does not matter. Okay. So then you call this these properties which are satisfied, you call this space to be a linear vector space, right? And this is satisfied in your 3 dimensional world. Okay, so there the condition is that if you give an arbitrary vector R, if I write this as a, so suppose each of those are given, and if this arbitrary vector R is a linear combinations of those vectors, or if you are given a set of vectors A, B, C and R, and if R is some linear combination of, let us say, Cn, or let me also write it as A times A plus B times B plus C times C, and if these coefficients A, B and C are 0, then you would say that the set is a linear independent. If A, B and C are non-zero, then this vector is dependent on the other vectors. You all learned this in your math course, right? So this is R is linearly dependent if A is not equal to B, not equal to C, not equal to 0. Could be the A, B and C could be equal, but I am meaning those scalar coefficients can be non-zero. Then you will say it is linearly dependent. Okay, so just to put it in a form of a flow chart or a set of points, so you can look at least in 3 dimensional space, in this physical space, how many linearly independent vectors you will have, right? I have said here 3 dimensional vector space, which is what we mechanically talk as x axis, y axis and z axis. Many times you won't even know what is the dimension, you have to figure it out in general, okay. So here the linear independence is the definition I have said, and you have to also know, if you are given a space, how do you span the space, okay. How do you span the space? Span means you should be able to write any arbitrary vector in using those spanning vectors, okay. Suppose let us take our the same familiar R3. So, this 3-dimensional space is sometimes called as R3. Okay, R3 is a notation where this 3 denotes x, y and z axis. Okay. So, here you could try to write that your familiar unit vector Ex, Ey spans the space. Is that right? No. So, you need to add Ez. You need to add Ez which spans the space, and you cannot completely write Ex and Ey alone are spanning the space. You could have written Ex and Ey are linearly independent. Right? Ex and Ey are linearly independent, and to span the space which is R3, you need 3 of them. So, you should have a set of vectors which are linearly independent and what? And span the space. This is very important. You can't just look at a set of vectors which spans. This is not the only one which spans the space. You could have defined something else which spans the space. What is something else which need not be linearly independent? You could add things like Ex plus Ey. This also spans the space. But are they linearly independent? This set spans the space definitely, but not independent. Okay. So, you need a set which spans the space and linearly independent. So, there are 2 possibilities, at least there are many possibilities. You could have Ex, Ey, Ez. I will put L dot I as linearly independent and span space. You could also have something else like Ex plus Ey by root 2, Ex plus Ey plus Ez by root 3. Why am I putting the denominator? So that they can be like a unit vector. Are these also spanning the space? They are also spanning the space. Are they also linearly independent? Any arbitrary vector, you can write it in terms of these 3. So, you can actually list, you can keep going. But you notice something in this keep going. What is something which you notice? The number of states which is linearly independent and spanning the space is always same, right? So, basis set is actually vectors which are linearly independent and span the space. Basis set. So, this is one basis set, this is a second basis set, and what is the difference between the basis set and basis set 1 and basis set 2? So, this one is orthogonal, the vectors are orthogonal, basis vectors in the set, whereas this one is still a valid basis set, but not orthogonal. Is that correct? still a valid set, but it is not orthogonal. Okay. So, you can work with any basis, not a problem, but conventionally whenever we do all our vector calculus and so on, we prefer to work with orthogonal basis set. Basis set is a set of independent vectors which are linearly independent and could span the space. The number of such vectors in the basis set is the dimension of V. Here I have taken this vector space to be a 3-dimensional familiar R3, but whatever I am giving you here can be extended to an arbitrary vector space where this number will change. It will not be 3, it could be many, but it has to satisfy these properties that they should be linearly independent, and any arbitrary vector if I give you, I should be able to write it as a linear combinations of the set which spans the space. That is why it is called it spans the space. If you have both the condition, then that minimal set is what is called as a basis set, and the number of vectors in that basis set defines the dimension of the vector space. Okay. So, given a vector space, for example R3, you can find linearly independent vectors. You could have 2 linearly independent, you could have 3 linearly independent, but you should also make sure if it is 2 are linearly independent, can it span the whole space, or any arbitrary vector can you write it in terms of 2 linearly independent vectors? That is not possible. So, you need to take count of both spanning the space as well as the number of linearly independent vectors, and then this collection of linearly independent and which spans the space. So, the linearly independent vectors and which spans the space defines the basis set. The number of vectors in the basis set defines the dimension of the vector space. Then the next question is, you can ask, what is the length of a vector? How do you do this in your vector calculus? Whenever you are given a vector A, if you want to find the length of the vector, you define A dot A and take the square root. This is what you will say is length of vector A, which is formally sometimes written as norm. This is what we call it as norm, which is nothing but square root of A dot A. Sometimes people also write in this vector calculus as vector A, magnitude of the vector A. Is that right? But in this process I have brought in some concept here. I introduce a dot product, right? I have brought in dot product, and what is the property of the dot product? If I take one vector A and another vector B, if I put in a dot product, this will give me a scalar. What is a scalar? A scalar is one. If you rotate your vector A and rotate your vector B by the same angle, then the dot product will remain the same, because the angle between those two will remain the same. Okay. So, that is why a vector, why is it called as a vector? If you do a rotation, then you know how it will transform. You know how the vector A under rotation, suppose I point the vector in one direction, you know how it will transform? Under rotation by some angle about some axis. So, it will go to under rotation, it will become a new vector. A will become a new vector, B will become a new vector, but A dot B will remain the same. So, it is a scalar. And when B is equal to A, you get the definition of a length of a vector or norm of a vector. And these are things which we need to have a handle. That vectors, length of a vector, dot product of a vectors in 3 dimension. And how do we go to an abstract notation is what we should see. Now, okay, with this knowledge on 3-dimensional R3, we would like to go to an abstract linear vector space, which is a V. How to find the basis set? Looking at the basis set, number of bases in that set, number of vectors in that basis set will give the dimension of the vector space. How to define a dot product? What is dot product called in an abstract linear vector space? How to find a length of a vector in a linear vector space? So, these are things which we would like to get a handle of, and that is called as a tool in quantum mechanics. If you understand that tool, we will be able to do things much neatly and clearly, and that is a universal language which most of us are following in the world, and I want you to learn that notation. Okay? Is this clear? It's all known to you. I am just putting the notation so that when I go to the abstract space, you are clear with the analogy. Okay, so the norm of a vector will always be positive is something which you all know, the length of the vector. The mod, magnitude is never a negative quantity. So, this dot product is sometimes called as an inner product, or most of the times in quantum mechanics we do not call it as dot product, we call it as an inner product. We will come to it. The inner product is one which will give you a scalar, which is what we saw, the dot product gives a scalar, and we will call this as an inner product.